Hi, good morning, good afternoon to everyone here. My name is Zoha. I'm based in Dubai, UAE, and I'm studying mechatronics engineering. I will be taking this opportunity to present my research titled A Review on 3D Printing Graphene Aerogels in the Field of Electronics that I undertook this past month under the extensive support and guidance of my mentor, Dr. Marcelo Setano. In this presentation, I shall go through what an aerogel is, some unique properties of graphene, how 3D printing is a feasible and efficient way of manufacturing graphene aerogels, and how this super material is set to revolutionize the electronics industry. So, to begin with, here is a statement from Mark Miodonic, a famous British material scientist and an awardee of the Royal Society of London Michael Faraday Prize, who conveys the importance of aerogels and what makes it such a fascinating material. For if ever there was a material that represented mankind's ability to look up to the sky and wonder who we are, if there ever was a material that represented our ability to turn a rocky planet into a bountiful and marvelous place, if ever there was a material that represented our ability to explore the vastness of the solar system while at the same time speaking of the fragility of human existence, if ever there was a blue sky material, it is aerogel. So, what is this aerogel that he speaks of? Aerogel is a term that is coined to a geometry which a substance can take on, and one that is removed of nearly all of its air, yet it retains its physical structure. As you may have noticed, I had also spoken of graphene in my title. I'm sure you must have heard of graphite, which is commonly used as the core in pencils. Graphene is similar. An allotrope of carbon, it is an atom-thick layer of carbon atoms arranged in a hexagonal lattice forming a two-dimensional material with exceptional mechanical, electrical, and thermal properties. Now, combining it all, an aerogel of graphene manufactured through a seamless additive manufacturing, which is also known as 3D printing, would result in advancements in a varied array of fields, most notably electronics. So let's start off with aerogels. Aerogels of all sorts hold records for different properties. Say silica aerogels. These materials hold records for being solids with the lowest densities at just 0.0011 gram per cubic centimeter, having the lowest optical index of refraction at just 1.002, where even the optical index of refraction in water is 1.33, and for having the lowest thermal conductivity among so many other special properties. In the case of carbon aerogels, these are well known for having some of the highest specific surface area for a monolithic material at 3,200 meters per gram. With that being said, aerogels of different substances offer a broad range of properties specific to the material. Aerogels are typically made by replacing the liquid component of the gel with a gas, which gives rise to a solid with extremely low densities and thermal conductivity. Such a super material, which houses so many distinct properties, such as being the strongest or the lightest material in the world, sets it apart from all other materials that exist today. Presently, aerogels have been used in the twin Mars exploration rovers, Spirit and Opportunity, to combat the extreme temperatures of Mars, which can range anywhere between minus 220 degree Fahrenheit to 70 degree Fahrenheit, and can result in extreme temperature gradients and thermally induced stresses in sensitive electronics. Aerogels have also been proposed for the use in oil spill cleanups and are being developed commercially for this application. So let's head on to graphene. First discovered in 2004, graphene is now considered a wonder material. It is one of the most promising nanomaterials because of its unique combination of exceptional properties. It is not only the thinnest, but also one of the strongest materials, and it conducts heat better than any other material. It is also an excellent conductor of electricity, is optically transparent, yet so dense that it is impermeable to gases. Not even helium, the smallest gas atom, can pass through it. Graphene is hailed as one of the most important breakthroughs in materials since the plastic revolution because of its potential applications in nearly every field to exist. It could create super fast telecommunications and electronics, and when mixed with plastic and other materials, it could create new kinds of light, flexible, and strong products. from planes to tennis rackets to even touch screens. The possibilities are endless. Some of its current and future applications include graphene transistors, something that Samsung's Advanced Institute of Technology has been experimenting with, that would allow for easy production of flexible displays on both wearable devices and headsets. Graphene is also resistant to water, so this material could potentially usher in a new generation of waterproof devices whose chassis may not really need to be sealed like the ones we have today. Alongside this, a new lamp was developed at the University of Manchester in the UK, where graphene was first discovered more than a decade ago. This lamp features a filament-shaped LED coating in graphene, which promises lower energy emissions, longer lifetime, and lower manufacturing costs. Now that we have heard so much of graphene and of aerogels, what if we incorporate graphene in the structure of an aerogel? We would now be resulted with what we call graphene aerogels. This superior material has so much potential that it can outrun the technology that we have in place today by a very large extent. So much so that Annemiek van Vleuten, a participant of the Dutch cycling team in the 2020 Olympics, wore a graphene-based shirt that employs thermal planar circuit, which is basically helps to absorb heat that is produced by the body and distribute it throughout its material, which keeps her warm. Fortunately, she ended up winning a gold for the Netherlands and for all of the material scientists who witnessed it. This shows that aerogel graphene is currently being utilized and used in various fields already, and its progress is still ongoing. Such innovative technologies with regards to graphene aerogel are being experimented and tested with, and the material will soon come across many more such industries. Graphene aerogels or GAs are gaining popularity specifically for their high strength to weight ratio. So even if you were to stack 150 blocks of GA one on top of the other, it would still weigh less than a gallon of water because it consists of nearly 98% of air. It is also way stronger than steel despite being less than 0.2% of its weight. Now, graphene aerogel also holds the record for being the least dense 3D printed object in the world. So among the most efficient ways to manufacture graphene aerogel is additive manufacturing, or simply put, 3D printing. Additive manufacturing, based on a variety of printing technologies, is considered as one of the pillars of the third industrial revolution. This rapid prototyping is used for directly manufacturing three-dimensional parts by stacking layers of material in order, allowing for nearly endless rapid prototyping possibilities. It has several advantages, such as design freedom and complexity, flexibility, and even high durability. When it comes to producing graphene aerogel using the 3D printing technology, there's two main types, among others. One being the direct ink writing, and the other being stereolithography, which is basically, in short, SLA. The main difference between the two is that the extrusion-based direct ink writing technique utilizes graphene-based liquid inks, so it's just normal printing, whereas SLA or stereolithography prints 3D structures using photocurable materials. Direct ink writing is based on the extrusion of materials that involves the deposition of liquid material ink, which is quickly solidified by extrusion. In order to get a smooth surface, the ink is required to have an appropriate module to conserve its shape after the extrusion. Inks with graphene are being reported to have better electrical, mechanical, and biological properties that can improve a broad spectrum of 3D applications. Despite the fact that this superior results have been obtained in using this direct ink writing methodology, there are still significant issues that need to be resolved even before they can realistically be implemented. So there are a few issues such as dimensional accuracy when printing complex patterns, and that require specific size and the resolution to impose a significantly small, simple structural unit without increasing the printing duration or reducing the geometry of the printed parts. On the other hand, stereolithography or SLA is the first 3D printing technique that makes use of laser light to cure photopolymer resin that is layer by layer. The exposure of the printed resin to a digital light projector would contribute to the formation of a solidified casual pattern in the resin. After the displacement of the platform, another layer of resin would be deposited and then solidified at the desired location. The final 3D structure would then be obtained after draining and washing off the excess resin. In comparison to directing writing, SLA can fully design printed objects of nearly arbitrary shapes, but it has a very, very slow printing speed. However, the resolution, manufacturing speed, and feedstock material limitations call for improvement in the technique. Speaking of the rheological requirements, the ink usually refers to a liquid or a paste with suitable viscosity and rheological properties, specifically for inkjet, screen, certain types of 3D extrusion, or photopolymerization printers. So depending on the printing technique, a functional ink is used, usually composed of the active material, additives, and solvents. Some of the main requisites of the rheological properties of ink are low viscosity, shear thinning behavior, good wetting properties, good stability, and the appropriate angle frequency. So the charts that you can see that are displayed depict different types of graphene oxide inks and how they perform to tests with respect to viscosity, with respect to shear rate in the first diagram, storage modulus, and loss modulus as functions of shear stress and angular frequency in the second and third respectively. So as iterated before, there are numerous current and potential applications of graphene aerogels in all fields of work. Here I should elaborate more on the applications within electronics. To start off, graphene aerogel-based energy storage devices have a huge scope in electronics industry, especially since they offer excellent electrical conductivity and high surface area, which makes them promising materials for use in electrodes for batteries and supercapacitors. Graphene aerogel electrodes can provide higher energy densities and power densities than traditional electrodes, which could lead to the development of more efficient and powerful energy storage devices. Going to lithium sulfur batteries, GA-based or graphene aerogel-based lithium sulfur batteries also hold great possibilities. Graphene aerogels can be integrated into lithium sulfur batteries in various ways, including as conductive scaffolds, sulfur hosts, and electrolyte additives. By serving as conductive scaffolds, graphene aerogels facilitate efficient electron transport within the battery system, mitigating the common issue of poor electrical conductivity in sulfur-based cathodes. Additionally, these aerogels can accommodate a significant amount of sulfur, acting as efficient hosts for sulfur storage. This can help in preventing the dissolution of polysulfides and subsequent capacity degradation, which is a very, very common problem in lithium sulfur batteries. Supercapacitors, also known as ultracapacitors, is an energy storage device with a large capacity, much like batteries, but they have the ability to hold substantial energy. GA composed electrodes have achieved very efficient storage capacity and charged and discharge stability, especially in the field of electrochemical energy storage. As an important dependency of a supercapacitor device, the electrode material is crucial to its performance, and the specific surface area and porosity of the electrode material are two very important factors to measure the performance of a double layer capacitor. Unfortunately, very few carbon materials can satisfy both the criteria, and as 3D stable porous carbon materials, graphene aerogels have very high electrical conductivity and strong mechanical strength, which provides a fast and convenient channel for the storage and transfer of electrons in EDLC, improving capacitance and efficiency. So graphene aerogels have come a long way from research, all the way from its first discovery back in 2004, and are currently at the developmental stage where this material is being tested to create more enhanced and sustainable products, especially in the field of electronics. Its unique properties, including high electrical conductivity, large surface area, and excellent mechanical strength, make it an ideal candidate for various electronic appliances. Overall, graphene aerogel is a promising new material with the potential to revolutionize the electronics industry. It is lightweight, strong, conductive, durable, and sustainable. As research into graphene aerogel continues, it is likely to find even more applications in sustainable products, and I believe this has a very bright future ahead. Thank you.
Are you